Welcome everyone to Dunbar High's fourth astronomy podcast. I'm your host Brandon, and I'm here with my co-host Daniel. Today we're diving into some pretty mind-bending stuff. Quantum mechanics. This branch of physics challenges everything we think we know about reality, from how particles behave to the very nature of the universe itself.
Right, so quantum mechanics can seem like a mystery, even for the most seasoned scientists. Today we'll explore how quantum mechanics works, its historical roots, why it's crucial for understanding not just the particles, but also the stars, galaxies, and even space-time itself. So let's start with the basics. What exactly is quantum mechanics?
So, at its core, quantum mechanics is the branch of physics that describes the behavior of matter and energy at the smallest scales, the atomic and subatomic levels. It is the physics of tiny particles like electrons, photons, and atoms, things too small to observe directly in our everyday world. And, unlike classical physics, quantum mechanics deals with the behaviors that classical theories just cannot explain, like duality and uncertainty.
Classical mechanics works well for big things, like planets and cars, but when we get down to the tiny world of atoms and subatomic particles, things get weird. Quantum mechanics explores phenomena like particle-wave duality, where particles can behave like waves. Secondly, there is the probabilistic nature of particle interactions, where we can't always predict exactly where a particle will be at any given moment.
And don't forget the discrete nature of energy levels in atoms and molecules. For example, electrons can only exist in specific energy states, rather than a continuous range, and they jump from one state to another when they absorb or emit energy. Now, let's take a look at the historical context that gave birth to quantum mechanics.
It starts back in 1900, when Max Planck proposed the idea of quantized energy levels to solve what was known as the ultraviolet catastrophe. This phenomenon had to do with black body radiation, otherwise known as the radiation from objects, and Planck's work laid the groundwork for quantum theory.
Then, in 1905, Albert Einstein stepped in and explained the photoelectric effect. He proposed that light wasn't just a wave, but was quantized into discrete packages of energy, which he called photons. This was a pivotal moment in quantum mechanics and physics because it helped solidify the idea that light behaves both as a wave and a particle, another very important and key idea in quantum mechanics.
It doesn't stop there. In 1924, Louis de Broglie introduced the idea that matter, like electrons, also behaves like waves. This was a huge shift in thinking. For decades, we had only thought of matter as particles, but de Broglie's wave-particle duality idea would become one of the cornerstones of quantum theory.
Finally, in 1926, Erwin Schrödinger formulated his famous wave equation, which provides a way to predict the behavior of quantum systems over time. Then, in 1927, Werner Heisenberg formulated the uncertainty principle, which states that we cannot simultaneously measure certain properties of a particle, like its position and momentum, with perfect precision. This uncertainty isn't just a limit of our tools, it is a fundamental property of the quantum world.
Now, let's talk about some of the key principles of quantum mechanics. One of the most famous is superposition. In simple terms, this means that particles can exist in multiple states at the same time until we observe them. A classic example of this is Schrödinger's cat, where a cat inside a box is both alive and dead unless someone opens the box and observes it.
Superposition sounds strange, but it's been proven in experiments. For example, in the double-slit experiment, particles, like electrons, create interference patterns, like waves, when not observed. But when we measure them, they act like particles, making them behave in a way we can predict. It's kind of strange, but this duality behavior makes quantum mechanics so fascinating.
Another mind-blowing concept is entanglement. This happens when two particles become entangled, meaning their states are directly connected no matter how far apart they are. If you measure one particle, you instantly know the state of the other, even if it's light years away. This phenomenon has been confirmed experimentally and is the basis for technologies like quantum teleportation and quantum cryptography.
So, with all these crazy behaviors, why is quantum mechanics so important? Well, it is essential for understanding atomic and subatomic processes. For example, quantum mechanics explains how electrons orbit the nuclei of atoms and how atoms emit or absorb light. Without it, we wouldn't be able to understand the fundamental interactions of particles within the standard model of particle physics.
And that's not all. Quantum mechanics has led to the development of technologies we use every single day, like semiconductors, lasers, and quantum computers. It's crucial for understanding the fundamental forces of nature, like electromagnetism and the weak nuclear force. They both give us a deeper insight into the nature of reality itself.
Now, let's zoom out a bit and see how quantum mechanics applies to astronomy. For instance, quantum tunneling is a key in understanding nuclear fission in stars. In the core of a star, temperatures and pressures are so extreme that classical physics would say that fusion just simply isn't possible. But thanks to quantum tunneling, particles can pass through energy barriers and undergo fusion, releasing energy that powers stars like our sun.
And when we talk about extremely dense objects like neutron stars and quark stars, quantum mechanics is absolutely essential. Neutron stars are remnants of supernova and are governed by quantum principles like neutron degeneracy pressure. This helps prevent them from collapsing under gravity, and quark stars, which admittedly are still theoretical, might be made up of quarks that aren't bound together, and quantum mechanics would have to govern their behavior as well.
Let's take a step further into quantum cosmology. This field aims to unify quantum mechanics with the general theory of relativity, which works for large-scale objects like planets and galaxies. Quantum cosmology is trying to explain the universe's earliest moments when both quantum mechanics and general relativity would have been at play.
One interesting aspect of this is quantum fluctuations in the early universe. These tiny fluctuations in energy during the inflationary period of the universe helped seed the large-scale structures that we see today, such as galaxies and galaxy clusters. As strange as it sounds, quantum mechanics may even be able to explain the Big Bang itself.
Exactly. One theory, known as loop quantum cosmology, proposes that instead of a singularity where everything breaks down, the Big Bang could have been a quantum bounce, a sort of rebirth of the universe governed by quantum effects.
And while we're on the topic of the universe, let's talk about dark matter and dark energy. These two mysteries make up most of the universe's mass energy content, but we don't yet understand them fully. Some of the leading candidates for dark matter particles, like WIMPs, otherwise known as weakly interacting massive particles, and axions, have both been predicted by quantum theories.
And as for dark energy, which causes the acceleration and expansion of the universe, there are theoretical quantum models that suggest that quantum fluctuations in a compact extra dimension might explain its existence. This could provide quantum field theory-based explanations for dark energy.
Now, things get even more mind-bending with the multiverse hypothesis. Quantum mechanics suggests that particles can exist in multiple states at once, and this has led some to propose the idea that our universe might be just one of many parallel universes, each with its own set of laws and constants.
In the Copenhagen interpretation of quantum mechanics, particles exist in single states until they are measured, causing their wave function to collapse. But the many worlds interpretation suggests that every quantum event causes a split, creating new branches of reality, each representing a different outcome. Essentially, every possibility is realized in a parallel universe.
And quantum fluctuations can play a role in the creation of these parallel universes. According to theories like eternal inflation, the small fluctuations in energy that happen at these small quantum scales could give rise to entirely different universes. So the multiverse might not just be a sci-fi concept, it could have a real basis in quantum mechanics.
This is where quantum mechanics really starts to stretch our imagination, especially when it comes to space exploration. Quantum computing has the potential to revolutionize the way we solve astrophysical problems, from stimulating the behavior of stars to modeling early universes. Quantum sensors can detect incredibly faint signals like gravitational waves or the movement of exoplanets with unprecedented sensitivity.
Quantum communication technologies, like quantum key distribution, can also secure data transmission over vast distances. This could be crucial for space missions, ensuring that communications remain safe from interception.
And we're still just scratching the surface. Recent advancements in quantum mechanics and astronomy, like the improved detection of cosmic microwave background radiation, are opening new doors to understanding our universe.
There are still a lot of open questions, especially when it comes to combining quantum mechanics with general relativity. But solving these mysteries could unlock new theories that reshape everything we know about space-time and the cosmos. The future of quantum mechanics and astronomy is full of exciting possibilities.
And that wraps up today's deep dive into quantum mechanics. We hope we've given you a better understanding of how this fascinating field shapes our view of the universe, from the tiniest particles to the vastness of space itself.
Thank you all for tuning into our podcast. We hope you enjoyed this exploration of quantum mechanics and the universe. Join us next time as we continue uncovering the broad range of different topics in astronomy.